everyone. Okay, so that was a technical difficulty. So let me just start again. Thank you everyone for joining our workshop. So today's workshop will be held by our very own Shopee data scientist, and I'll be introducing him in a bit. So to help us run the workshop smoothly, do submit all your questions using the Q&A function in the Zoom taskbar below. And also if you have any urgent requests, please use the raise hand function. So we will try our best to attend to your requests or any issues if we see this raise hand function. And then next, before we begin, this is a very quick administrative slide. So to optimize your Zoom viewing, please click the side-by-side mode and also use the speaker view so that you can see both the speaker as well as the speaker's slides. So on this image here, you can also see that Zoom, they have a glider bar here. You can also adjust the size of the speaker view as well as the presentation slides. So you can adjust it, until you're comfortable with the view. Okay, so now let's move on to the actual training workshop. So I'd like to introduce our data scientist from Shopee, Xiaoyu. So Xiaoyu, you can take over now.
Okay, thank you guys. Can you see me? Okay, perfect. Let me share my screen. Okay, nice. Hi everyone. Thanks for coming today's training workshop. So today's topic is going to be something related to natural language processing. So I'm going to go through the following contents in today's sharing. Basically, first I'm going to give some introduction about what is like NLP and how is the NLP used in the industry field. And also I'm going to give some introduction about basic text processing and also NLP theories. So that is like related to how you process text related to problem, and also like some basic problem theory about natural language processing. And then the third part, I think most of you may interest about the models. Some is machine learning models or statistical model you may use for general NLP tasks. And the last part, I'm going to introduce some of the popular NLP engineering frameworks you may use in the future. Okay, so let's jump into the first part, overview of NLP in the industry field, right? So in fact, like NLP, natural language processing, is like one of the subtasks of machine learning. So before we jump into natural language processing, I'm going to give some introduction about what is machine learning, right? So people talk about AI, artificial intelligence, talk about machine learning every day, but in fact, like machine learning is so from Wikipedia, right? Machine learning is a study of the computer algorithms that improve automatically through experience. So in fact, the process of the machine learning model is quite like a baby learning stuff, right? So here is a basic learning process for most of the machine learning tasks. So the first step is always about data, right? So when we talk about machine learning, is like most of the data science is like say, okay, we have this kind of data, we have that kind of data, we solve a certain task, right? So the most key part is the more time is like the raw data. You get the raw data and analyze it. Then you want to like have a model to help you solve problems, right? So the second part is called data clean. It's always data clean, very important. So for most of the time, right? So for most of tasks, for data clean, it's like 60 to 70% of the time of the data science is like do the data cleaning work. The reason is that right now we have lots of fancy models, very powerful models. So even with so many powerful models, if your data is very dirty, it tends to give you some of the result is not that good, right? So basically one of the tips or recommendations to your guys is like when you deal with a machine learning problem, always spend more time as looking to the data and do the data cleaning work. Then fit into your model most of the time, then you can get a very decent result, right? So the third party, like most of the training part, you have some models, then you have the data. You hope the model to learn something, right? So it's something like the high school, right? You have the linear regression problem. So basically you have a bunch of points, right? So basically you want to have some mathematical function, y equals wx plus b. You want to learn about the w and what is the best w and b for the function, right? Then like in the future, you have some new data, you can fit into the model and get the result. So here is like basically the process of the machine learning models. So when we talk about machine learning models, it's most time is like the machine learning model is like it's trade-off between underfit and overfit. You always want something like optimal here, right? So the reason is like the machine learning model can sometimes overfit is like because it tend to have so many parameters. If you give them all the training data, it's like tend to perfectly like fit into each point, like this one I show here, right? But when like you jump into something it's never seen before, the model is so say like not robust enough to predict the new data. So that is like something you need to look into either by careful cross validations or you do some extra tricks to avoid the model being overfit, right? Then we jump into our today's topic is like natural language processing, NLP. So NLP is like here is also a definition from Wikipedia. It's a subfield of linguistic, computer science, and AI, right? To concern with the interaction between computers and also human language. So in fact, like sometimes you say, okay, it's not hard, right? So we every day or human beings use language to communicate, right? We talk to each other. We use language to communicate. We write in books through language. Why like so hard? Like so it sounds like not that hard, right? But in fact, like because the computer is like most of the time it don't understand the language you're talking about, right? So here's like one of example. When I talk about welcome to Shopee Code League 2012, you understand okay what's the meaning of the sentence, but for computer it's just bunch of the characters. They transfer that into numbers, then they save into the memory. So they don't understand anything about the contents. So that's the difference between the human beings, right? And also the computers, right? So regarding to the natural language processing, we want to teach computer to understand the things we're talking about, right? When we talk about this sentence, they can get some meaning from it. So that's the purpose of the natural language processing. Then we jump into some main categories of NLP. So the first one is the speech recognitions. So basically, it's like lots of the main company like Google, they have the Google Assistant, and also have I think if you have an iPhone, you have a Siri inside, right? So basically, it's transfer your language when you speak. It's understand some of the speak, and then you give a question, and also the software are going to give you some answers. So the speech recognition, in fact, is like one of the main tasks like right now, like lots of companies is working on. In fact, like it can be quite convenient for you to have this kind of functions. So here is like one of the examples like Google shared before. They use this kind of Google Assistant to help them to book a restaurant.
Hey, how may I hear you?
Hi, I'd like to reserve a table for Wednesday the 7th.
For 7 people?
It's for 4 people.
4 people when?
Next Wednesday at 6 p.m.
Oh, actually, we reserve for like after like 5 people. For 4 people, you can come.
How long is the wait usually to be seated?
For when, tomorrow or weekday or?
For next Wednesday, the 7th.
Oh, no, it's not too busy. You can come for 4 people, okay?
Oh, I gotcha. Thanks.
Yes. Bye-bye.
Okay, so basically the man's voice is like it's in fact it's a robot. So basically the robot is helping like the guy using the robot to do to book a restaurant. So you can see like it's totally understand every set questions the waitress given, and also give a very good as a perfect answer to it. So it's like so you can see like basically it's one of the amazing application of speech recognition in real life. And also another topic is called natural language understanding. So basically, if you use Google Translate and all the translation software, you deal with this kind of machine translation problem. So basically, they use this kind of algorithm to help you translate the language from one language to another one, right? And also question answering. Basically, you can ask some questions and hope the robot or the machine to answer the question for you. And also text categorizations. In fact, it's like this category including lots of tasks in our daily life. The third one is natural language generations. So since like human being, like it's like very long history ago, right? We writing stuff. We write articles. The human beings write articles, write fictions, such as Harry Potter, right? So like one of the target, like, in fact, is for the machines, like whether it can generate some language, generate some articles or poems, it like can close to the human beings, right? In fact, it can right now. Here is one of the examples that generated by GPT-3. So I have set as the price for this, just looking. So like it's basically, if you don't have the sign here GPT-3, you maybe imagine like, okay, it's from one of the very famous guys to write this kind of poem. And in fact, except for generated like human beings language, right now, like using this kind of very powerful GPT-3, which developed by OpenAI, it can also generate is like regular expressions. So here is one of the examples, right? So you give a description here, find a valid URL that starts with HTTP or HTTPS. Then you give some examples. Then you just hit generate. The robot automatically is generate this kind of regular expression from rules for you, so you can use directly. So basically, in order this kind of GPT-3 to generate this kind of regular expression, it needs to understand what is the things you input, and also get this kind of examples, right, to get a final result. So basically, it's an amazing task that I did by GPT-3 and OpenAI. So we jump into the next topic. So basically, there is like three category mentioned, but it's like in our daily life. In fact, lots of places we use this kind of NLP technique. The first one is spam detections. So spam detection is a very important task in our daily life, because most of the time you get let's say like dozens of the emails, and for some professors, right, they even get hundreds of emails per day. So you want to keep the useful information, right? Useful emails such as, okay, today is a Shopee Code League training session. Okay, it's like maybe in some days you get offer from the Shopee. So you for sure you don't want to miss that kind of emails. But also, on the other hand, you want to remove the spam emails, right? Because it takes so long time, you just click into each email to check the result. So in fact, there is various ways to do the identify spam emails. Right now, I think lots of companies already did very good work. So here is one of the examples. You can use something called naive Bayes to do that. So the idea is that you look into lots of spam emails, and also you look into lots of emails it's not spam, right? Then you calculate something is called conditional possibility. So basically, you have this kind of possibility here is like it's given a certain word or certain sentence, what is a possible probability is going to be a spam, right? So basically, you based on all the information you have before, you look into that, and then you get something like a spam dictionary, right? So here are like some examples or some of the most highest probability spam words like going to happen for inside of emails. One is once in a lifetime, and also order now, please read special promotions. So you don't want to include this kind of words inside of your emails. So like in the future, it may go into the spams. But also you can try some very fancy machine learning technique, right? So basically the idea is that, okay, you have this kind of spam and on-spam emails. You do a vector representation of each of the words. So basically I'm going to introduce this kind of things later. It's called word to vector, how you transfer a word into a vector. then you feed in that one into a classification model, then you have this kind of result, whether a certain email is spam or not, right? So let's jump into next application. So I think everyone use Google search every day, right? Search functions. So basically one of the important application is called autocomplete. So autocomplete is like something you type into something, such as you type into natural language, right? So it's going to give you the whole sentence of that, right? So basically like from Google, right, they say that, okay, by using this kind of autocomplete functions, the user can save up to 25% of typing time, right? Even when you use Shopee app, there is lots of functions use this kind of autocomplete. So when you jump into the address page, right? So basically, most of the time the address you type like can be very long and routine, right? So you want to save time from that. And also like from our perspective, we also want to save from the time from the customers. So you can spend more time like to look into the products, right? To find the things you want. So basically here is like one of the examples. You type into something, we give recommendations of the address or certain address. So you can save time, right? Typing the rest of the words. In fact, based on the analysis, these functions can save up to 50% of the typing characters from the users, right? So the third one is the search. So something like different search is like when you search inside of the Google, right? So basically it's going to, based on the text you have here, and also based on some your previous searches or search habits, right? To give something useful here. So in order to give a very good result, they use various models, and recently they use something is called BERT. I'm going to introduce in later this sharing session. So basically, it's tend to let the search engine to understand all the information is like input and give a very good result. It's like personalized result to you. And the third, this one is like grammar check. If you write papers and write stuff, and also if you are bad grammar, like me, like most of the time I write something like have the grammar issues. So basically, this kind of tools, such as Grammarly, can help you to solve the typos and also give you some advice how you correctify the sentence. Right. So the last one is we did it. I use is a chatbot, right? So I'm not sure. I think most of you guys have the similar experience like me. It's like you call some service, right, online service, and then it's like waiting for about half hours, and then it's like just keep giving, okay, please wait. It's like it's our customer service will come back to you sooner. But after half hours, like suddenly the call is like help, and then you what happened to it? So basically, chatbot is also one of the main things most of industries work. So also like for Shopee, we also have this kind of chatbot here is like Sophie. So you can ask Sophie about anything you want, like where is my order and how can I cancel my order stuff. So basically, it's have lots of advantages, such as you have higher return speed, right? So you don't need to wait for long calling, and also reduce operation cost from the customer, and available 24/7, and also improve customer satisfaction. Right? And so we jump into the next part is the basic of text processing and NLP theories. So the idea, the first one is like how we represent a word. So beforehand, like we have lots of words. So people like try to just write down words and also type into sentences. But when we talk about like NLP, natural language processing, first we need to represent a word in something like computer can understand, right? So the first like traditional NLP, like they use this kind of discrete symbols to represent a word. It's called one-hot encoder. It's like if you familiar with machine learning, it's called one-hot, right? So the idea is quite straightforward. You have this kind of array here. So for this array, for each of the position is represent one word. So here is one of the sentence, Shopee colleague welcome you, right? So for the when talk about Shopee, then you can imagine like it's bunch of signals, right? Signal signs. then like suddenly it jump one of the signal is like highlight. It means okay, here is a Shopee, right? Then you jump into the second word is like this signal is like highlight. It means it's a code. So for each of the word, it's going to have a like specific position here to represent the word, right? So in fact, like this one is like can solve some more problem, but it also can cause some more problem. So first, like because we use this kind of vector, right? But if you look into the vector, it's quite sparse. So I mean sparse here, like lots of the positions is 0, right? So when we deal with vectors, we deal with matrix. We don't want sparse matrix because like you can see that lots of a position, you occupy the memory, occupy the space, but it's just like something you don't use, right? The information like it's just zeros, right? And also it's like dimension is like keep increasing with words. Let's say like right now you have millions of words, but we know like every day like people tend to create new words from different language, and also one of the important part is like people like missing some character inside, and also people have typos and also have abbreviations. So if you consider all of this kind of stuff, then the arrays is going to be huge, right? So basically that is like something like the problem of the discrete symbols or one-hot encoders. And also another thing is vectors are orthogonal to each other. So basically every dimension, so orthogonal is perpendicular to each other. So basically it means Shopee to, let's say like if you have a word, right, dog and a cat, you hope the dog and cat vector is much more close to each other rather than dog and apple, right? So basically that's something like this one cannot consider inside. And then like we're going to the next one, like how we solve the problem is like, but when we look into the word, right? So what is the true meaning of word? So let's give an example is like here is like dog. So we talk about, I just say dog, right? So the things jump into your mind is sometimes like, okay, it's first one is synonym, right? It's a puppy, like something such as a dog, right? Then you also look into something like similar to dog, right? It's like car is like compared to apple is like for sure like something like jumping your mind is first, and also have some like superordinate and subordinate, right? So for superordinate, you consider about animal, right? For subordinate, you consider a subtype, like, such as bulldog. So in fact, like when we talk about certain word, it's like we consider lots of stuff. So here is like one of the sentences given by Zelig Harris. So in fact, how we define a word is like if A and B have the almost identical environments, we say they are synonyms, right? So basically, the meaning of word is defined by the environments is nearby, right? So here is an example. Then let's have a seat and watch the puppy dog parade, right? I will always want a dog. In fact, like when we change this one to puppy, right, it's work. And also if we change that one to a cat, these two sentences also work. But if you change that one to something like apple, like it's going to be super strange, right? So like people don't like sit and watch a puppy apple parade, and I also like don't have the case. Like I think like sometimes you want an apple, but it's just don't like it's not common. You always want an apple, right? So basically, whether like we can use a vector to represent a word. So in fact, like it's called how one of the method. It's called word vectors. It's also called word embedding to represent one of the word. So here is one of examples. So you use a array of the use a vector of the values to represent a certain word. Right here is an example. Is like you give a dog, you have this kind of vector here. So the idea of that is like, so as I mentioned, right? So the meaning of the word is depends on the nearby environment, right? So whether like we can use this kind of dog to predict the nearby words. So this is some method is called skip grams. So basically it's like you have this kind of a so-called central word. Central word is a dog, right? So based on the central word, you want to increase the possibility of puppy and outside of like nearby the dog, because like so here is like the puppy here, like perfect position. But if you change apple here, it's just not suitable, right? There is a apple dog or something, it's not work, right? So basically the idea is that, if you have the central word dog, so you want to increase the probability, is like the sum of the convenient word is nearby. So here is like the mathematical representations, right? So basically, just reminder, okay, the sin stands for the central word, right? So you have this kind of probability, is like given the central word as a position t. So here is dog, and what is the probability of the t-1 word, right? So here is like the probability definition. So it's something is called softmax, right? So basically you have vector represents the central word, is vector C here. You also have a vector, something like that, to represent the outside word here, right? So you multiple both of the vectors, you have one of the values. So the idea is that like you want this kind of values is going to be big when like here is a puppy rather than the outside vector is apple, right? So basically this one is called probability, conditional probability. So basically you calculate all the possible combinations. You have the central word, you look into the you have a dictionary of all the words, right? So you calculate all this kind of exponential inner product of the two vectors. Then you sum of them, then you have a probability of this kind of outside word with this central word. So you want, so as mentioned, right? So you want this function is as high as possible for this kind of common words. So the idea is that is you jump into bunch of the text, right? So basically, it's this one is called unsupervised learning. So basically, you jump into a text and you jump into lots of such as news and also fictions. So you have all the words, right? Have all this kind of sentence. So you train a model, train this kind of probability based on the word you have, right? So basically, here is the objective or cost or loss function. So basically you go through the central word one by one. So you won't have the reduce the cost function. If you look into here is have the minus sign. So you want to reduce the cost or loss function based on all the document you have, right? So that is something is called scalegrams. So basically the idea is that you want to increase the condition possibility of the outside words given a certain word and also meet certain based on your document, right? So here's a idea. And also another reverse idea is something called continuous bag of words. So basically that one like it's reverse, right? So you have this kind of nearby word, right? You have a puppy outside of, you want to increase the possibility of the dog happen here rather than apple happen here, right? So it's a reverse idea that is like you want to increase this kind of possibility. So here is like two of the main method to generate the word embeddings. So when we talk about this kind of cost function right here, right? So there is the something you want to get like for the final result is that it's going to be vector, right? So basically each of the words is going to have a specific vectors, right? So and then like you have a bunch of words, so it's going to have you have a matrix for that. So the idea is that you want to here is the parameters you have, right? So basically every time you jump into a new word, you get a vector from this kind of parameter. You want to reduce this kind of loss function, right? So basically you want to reduce, you want to have a better, this one parameter is like learning slowly, and then you want to reduce the cost, this function, right? So this one like is something like called gradient design, or like it's called optimizer. So basically you have some of the parameters, then you want to reduce the cost. So here is the definition is gradient design. So you update your parameters in a negative gradient directions to minimize the loss. So here's the examples, right? So you have the cost function here, and also you have the parameters here. So the idea is that, okay, your cost function is like right now here, right? So the idea is that how we can adjust this kind of parameters, right? To slowly, then we have a lower cost. So the idea of the gradient design is like, here's a gradient. So the definition is the gradient is like the part is like your cost function is going to increase, right? So it's like going to be this direction. And for this part, it's going to be this direction. So the negative gradient direction is going to be this one, right? This direction for your parameters. So you slowly go this direction, slowly, then you get your minimum. So in fact, like why like here like have this kind of alpha here is like called learning rate. Why we want to do that, right? Because like, so when you do the gradient design, you maybe like you just want to jump directly here, right? Jump directly here and then get the minimum. But the true situation is not that. So if you have something like you didn't control the learning rate here, it's like have high possibility you jump directly to here. If you say the cost function, in fact, the cost function is like cost is increase. So that's why like for this kind of gradient design, you need to control or fine tune the learning rate here. So in case you have this kind of overshoot problem. So also like in real, in real applications, sometimes the gradient, this part, when you calculate this gradient part, it can be time consuming. So in real industrial, like when you do some applications, in fact, it's like most time we use something is called stochastic gradient design. So basically you have, let's say you have millions of training data or millions of data, but you slowly you take one of the so-called batch. Let's say you take 1,000 sentences first, then you update your gradient a little bit based on that gradient, right? You update your parameter a little bit. Then you take another 1,000 sentence, then you update that one again, right? So slowly, you get into the minimum of the cost. So that is a part of like stochastic gradient. So you don't want like you wait for a very long time. It's like the gradient just update one time, right? So that is the idea of the SGD. In fact, it's a single stochastic gradient design is like belong to something is called optimizer. So in fact, it's for most of the machine learning problem. So you define something like first you define a loss function, such as here, right? You define a loss function, and also you define optimizer. You let the optimizer based on your function to do the optimizations, right? So the idea is that, as mentioned, is like single stochastic gradient design have lots of problem, but it's truly like for most of daily work, like still is like can give a decent result. So basically, it's one of the common use optimizer, but the problem is that it's need to tune the alpha. If you remember here, right? So you have a learning rate here you need to tune. So basically, it's a predefined by human beings or from us. So this one, like most of the time, you choose a very small one first, then you smallly like adjust it. So basically, this one is something you need to adjust yourself. But whether like we have other ways to solve the problem, right? So other optimizers is trying to solve the problem of the stochastic gradient design. For example, is like other grade. So it's called adaptive gradient. So basically, it's slowly. It's like you don't need to define alpha. So basically, you just give an initial alpha, but then like the algorithm going to slowly update the learning rate for you, right? So if you look into this example here, right? So basically, you have the white point is the represent algebra grade. So basically, for algebra grade, it's like it's here point is like it's okay. It's say the gradient is like it's not slope, so it like tend to slow a little bit. Then like at the later stage, it's going to go faster. And also other method like root mean square propagation, and also other it's all like different optimizers trying to like to give a faster convolution into the global minimum. So here like it's one of the GIF like trying to show the process, right? So basically you have this kind of X, Y axis is represent your parameter dimensions. But for the Y axis is going to be cost. So for the optimization problem is always one of the problem I'm trying to solve is like you want your optimizer is going to the global minimum rather than the local minimum, right? So here like you can see like it's not the cost that is still high. It's just compared to other stuff is lower a little bit, but you don't want your optimizer is like set into this part. You want it like go to a lower cost, right? So basically, also other algorithm, other optimizers such as Adam and other grad is trying to get into the global global minimum rather than the local minimum. So also like Adam is like one of adaptive moment estimation is one of the most common used optimizers in most of the deep learning problems. And then as we mentioned, okay, you have this kind of vectors, right? So you basically, you look into a bunch of the text and you train, you have this kind of theta here. It's a metric of all the word vectors. How you are going to see whether it's good or not. So in fact, like for most of us, like we seldom to train a word vector from start. Because like lots of company or like lots of researchers already did that task for you. So they train the word vector in some resources such as Google News and also Wikipedia's. So two of the famous one is one is Glove, which is developed by Stanford, and also FastText. So you get lots of vectors from different areas, and also some of the tools is also have an embedded word vectors inside. So basically you give a word is tend to give you one of the vectors. How you evaluate whether certain vector is good or not, right? So one of the things like to do is like it's called nearest neighbors. So you have this kind of two vectors, right? So you use something like when you measure about the vector similarity, or you want to measure how close two vectors, it's use something is called cosine similarity. So here is the function is that define the cosine similarity. Basically, you want the theta, the angle here like as close as possible when like two vector is close. So the idea is that here like one of the examples given by Glove. So basically, you input one of the vector of the frog, then you want the okay like the want the Glove to give you back all the closest vector to the frog vectors, right? So you find okay, this one is the frog, then you find the nearby all the vectors. In fact, when you look into the result, the first one is the frogs, right? So it's like basically the same thing as frog. Then the second one is the toad. It's basically like for me part is like also something like frog. And then you also have this kind of strange things here, right? So it's like Litoria, I don't know how to read this word. It's all something like different types of the frogs, right? So basically you can look into, okay, the word like truly like when like we're using this kind of vectors to represent word, it can truly learn the meaning of word. They know, okay, frog and toad is like much closer. They didn't give you something like apple, right? So basically this kind of vector like have some meaning inside. And another like things like most of the time like people tend to test whether the vector is good is called linear substructures. So one of the examples that people tend to give most of the time is like if I give you two words, man to woman, and similar like king to what, I think most of people is like jumping into man is going to be queen, right? So basically it's like some similar like relationship between man and woman to the key to queen, right? So the idea is that because we all like vector here, right? So basically we have each of the word, we have a vector here, right? So whether like we can do some linear substructures, we just use a vector, one of vector, subtract another vector and plus vector, another vector, whether we can get something similar, right? So in fact, it's amazing, like by using this kind of unsupervised like learning, it still give a very decent result. It's like when you use a vector of king minus man and plus woman, it's going to give you a queen as a closed vector to the result. So basically using this kind of word vector is basically can learn some meaning of the words, right? So basically what is advantage of the word vector compared to the Whitehall encoder we just mentioned? So the first one is like just because our NLP model right now is like use embeddings as representation of the word meaning. So basically you transfer the word into an embedding, then you feed that one into the model. And then also it's like reduce the saving space, right? So basically beforehand, like for so basically for the most of the vectors, you define a certain dimensions like 64 or 100. So basically you predefine or 33 dimensions. So all the things like going to just like limited, it's like you have this kind of matrix. The one dimension is like how many words you have. Another matrix is a dimension you define for the word vector. So basically it's a reduced saving space. When you have more vectors, you just increase one dimensions. But for the word one hot encoder, it tend to increase both sides, right? And also the third one is the have word meaning of the vectors, right? So basically as the two examples I just showed, so like it's truly learn some meaning from the words. Maybe let's jump into the Q&A to see what I like. Some questions. Yeah, maybe I just answer all the questions later. And also, before we jump into next topic, we are going to give some basic understanding about regular expressions. So as long as you deal with text and also deal with sentences, you need to have this kind of regular expressions to help you to clean the data. Here I just gave some very basic regular expression functions. So the idea is that you use this kind of a pattern to help you to filter, to find certain words, or you replace certain words inside of or you find certain pattern inside of the sentence, right? So basically, it's pretty convenient tools, and for sure you're going to use it. Here is like just some basic examples. So here, like you have A to Z, right? Big Z, it means match an uppercase letter. So when you look into the example here, welcome to Shopee Colleague 2012. So you use this pattern and you use a match function, right? So basically it's going to find the biggest, the first uppercase letter is in the sentence, which is a big W, right? Similar if you have this kind of area here is match a lowercase letter. So basically it's find the first lowercase, which is E here, and also match a single digit. It's like you find 2 here, and also you have this kind of symbol here is not an uppercase letter. So basically you find the first not uppercase, which is a smaller E here. And also have something more complicated is like you have the question mark here is represent optional previous chart. So basically you look into the character, whether they have or not have. So it's like 0 or 1 time, right? So basically if you have this kind of pattern here, it's tend to say, okay, whether it's shop or Shopee, right? So basically you can have a E here or not have E here. And then the star here, star is represent is like equal or greater than 0. It's like can happen 0 time or like several times. So basically you can have all these kind of combinations until you have infinite E after shop. And also this plus sign here means it's like 1 or more previous character. So basically you need to happen 1 time. So here is one of the example, right? So you need to have at least 1 E after shop. So you cannot match a shop here. In fact, like regular expressions have lots of complicated like representations. So you can look into lots of material if you use it. And also it's a bunch of study material and tools outside you can use. And then after I introduce about the word to vector, next topic we are going to introduce is so-called tokenizations. So like the definition is like you give a character sequence and define a document unit. Tokenization is a task of chopping into pieces so-called tokens, right? So the first is I heard that you may think, okay, it's not complicated, right? So because like for English, like we just, okay, so here the example, it's cost me about Singapore dollar 1.5 to take the MRT to Shopee, right? So so first idea is like, okay, we'll just split by space, right? Because it's the English here, and also we'll remove strange punctuations, right? Then you get your get your result here, like tokens by tokens. But it still can cause some problem. Like here, like some issues I point out. First, like you have the Singapore dollar 1.5 here, right? So it's like you split, because remove the punctuations, you split the 1 and 5 away, but you also keep it like together with Singapore dollar 1. So basically it's something like it's like corresponding to our human ideas, which is 1.5 should be together and Singapore dollar it should be together. And also you have this kind of clitics issues. So it's eights, right? So when you remove the punctuation here, it's going to become 8s, right? So basically, if you just use this kind of straightforward tokenizations, it's going to generate lots of s inside of your document. So basically, if you do some, for example, if you do your word to vector or you do your tokenization first, then like you can see like it's have some strange like s here. Is because like, okay, it's removed the punctuation, so it only left s here. And also I have a bunch of other methods, such as dictionary-based tokenization. Basically, you can do something like you save the Singapore dollar here, right? So basically, when you see Singapore dollar here, you split that out as one of the specific token. And also have the rule-based tokenization, which is based on the regular expressions we just introduced. You set lots of rules, such as, okay, is something before the certain punctuations or after a certain space, you have this kind of rule-based tokenizations. But it still can cause lots of problems. So even like use the rule-based plus dictionary-based tokenizations, it still cannot solve some of the problem. First, like some of the language, right? So here is like one of the language Chinese sentence, 虾皮让你购物更美好. Shopping use Shopee, right? Basically, it's like no space in between words. How going to tokenize it, right? So like it's for Chinese like it's tend to attend everything together. Then you have this kind of punctuation. So it's like very hard to split word by word or like word by word. And another thing is that it still cannot solve the problem of unseen word of a word to vector. So the idea is that if something you never saw before, right? So only use the space to tokenize, right? So you're going to have lots of words such as abbreviations or also typos. It's like you never saw before. Then you jump into the word to vector task. Then you're going to say, okay, lots of word it's never happened to your sentence, but then you still need the vector to generate. Then like it's an impossible task, right? So how we solve the problem? So here, like in fact, like when we human beings like look into the words, we do something in like called morphology, right? So basically, here is one of examples. You have unlikely, right? So the idea is that you split that one into different parts. First, you take all the IY, which is a suffix, right? And then you keep the unlike with stem. Then you split unlike again, right? Then you get the on like prefix, and then you have the like as stem. So basically, that is human beings like to look into the words, right? So why we do that is because we know is that ly is that most of the time it's happen as annual words. It have special meanings, and also like is un is have special meanings in the words, right? So we tend to use this kind of two words, two characters rather than just un here, right? That's how we split the word. So basically, use a similar idea. So it's like lots of scientists or like researchers like have different ways to do is so-called subword tokenizations. So one of the famous one is called bit pair encoding, is BPE. So here is one of the examples. So the BPE, like basically initially you start with bunch of the characters. You just split the word into different parts, right? So for deep, you have D, E, E, P here. Then you jump into, it's also an unsupervised task. So you don't have labels, but you have a bunch of text. Let's say you have Wikipedia, and also you have, let's say, Google News, right? So the idea is that you jump into the Google News or Wikipedia, you count how many times deep happens, how many times each word happen. Then you look into each of the combinations. Let's say, okay, you look into the combination of the DE of all the word you have, right? So the DE here is happens 3 times. And then also it's like models here, like DE happen 2 times. And the deploy here is happen 1 time, and models here is like the happen another 1 time. So basically the idea is that you calculate how many frequency certain word combination is going to happen. So you choose the one that have the highest frequency and use that one as a new gram, right? So-called gram. So basically you can get something like the one we mentioned, have the on here and ly here. So the idea is that by having this kind of grams, so in the future, even you have the new words, right? But you still can combine them together. It's like if you have a new word, let's say you have a deployment, right? So basically you do the DE as one of the token to that specific word, right? So it's something as the idea that like that. In fact, it's have a various method, but the idea, basic idea is the same, such as unigram language modeling tokenization and also word piece, which is one of the tokenization that used by a very famous language model called BERT. So basically, if you in the future you see something like this one is pretty strange, it means okay. In Hapatia, like this word, I think most of us we don't know. It's in fact it's a math. I forget, like it's a physics or mathematician like in Egypt history. It's a name. In fact, it's a woman's name. So basically, it's not a common words like we say in our daily life, but how we tokenize it, then you can see, okay, it's like split H all, then you have a YP here and ATI here and A here. Then you combine them together, you have your whole word. So the star here, the signal here is a represent, okay, it's going to link to the previous word, right? So then you have each piece of the word, then you combine them and you have the total word. That's how you do the word tokenizations. And in fact, like sometimes like the people just can use the pure character level. So for example, like for this kind of word is that just use HYPATIA directly, each separate characters. It sounds like it's an impossible task, right? Because you just take the character out, it's lost the meaning of the word itself. But in fact, like for some of the research, they find out using some of the deep learning models, it still can catch the meaning and also generate some of the reasonable result for some of the tasks. So yeah, after this is the first part we introduce about the basic of the NLP. Then like with all the knowledge you have learned before learning in the last section, we are going to jump into the next section. Is the methods we use for general NLP task. So just for a recap, like what is the most of tasks that we deal with NLP? So one of the tasks like I think we saw it is most of the time is a sentimental analysis, which is like you can treat it as a classification or regression problem. So the idea is that, so the difference between classification and regression is like classification, you have a certain label, whether it's true or false, whether it's positive or negative. For regression problem, you tend to give a number, whether it's like 50 or like it's 65 or something like that. So the sentimental analysis, like you give a sentence, you want to give a label, whether it's positive or like a value, how positive it is, right? So basically, this one like one of main tasks of NLP. And also you have the name entity recognition is also something like classifications. So here is the one of example. Ruby graduate from UIUC in 2017. So the text is like, okay, you need to recognize Ruby is a person, right? And then like UIUC, University of Illinois Champaign, which is organization name, and also 2017 is a date. So the idea, like, because for most of, let's say, like, it's in fact lots of application areas to use a combination of the NER and also sentimental analysis. So one of the example, like in stock, right? Lots of people like try to do the stock price predictions. So one of the idea is that you jump into lots of medias and newspapers, you get the organization name, right? So basically, okay, from this news is like talk about the Tesla, right? Talk about Google or talk about Shopee. Then like you do this kind of sentimental analysis to see whether the news is positive to the company or like negative to the company. Basically, you look into thousands of this kind of news. You have this kind of distribution, right? So you can guess, okay, most of the newspapers talk about good of the company or bad of the company. Then you do the investment based on this kind of NER and sentimental analysis. Another thing is like most of tasks like for NLP is called question answering. So basically, you give a question to the robot. It's like which company will hold 2012 Shopee Code League. It's give you answer, which is a Shopee, right? And also machine translation. It's a basically you have a sentence here, you give another sentence, right, from English to Chinese, and also another task is text generations. So basically, it's something like the task you did, I think it's a middle school or like kindergarten, right? So basically you give a part of the sentence, then you predict what is going to come next. In fact, like these three texts is all called something like language modeling. I'm going to introduce about that later. So we talked about machine learning beforehand, right? So basically, the task of the machine learning is like you have the training data, and do the data cleaning work. And so one of the specific part about machine learning is that you need to do something is called feature constructions. I think most of you guys like deal with some of the machine learning problem, either classification or regression. Use some of the famous tools like XGBoost and also LightGBM, right? So very famous boosting method or random forest. And then, so basically one of the main tasks is during the process is called feature constructions. So this part is like need lots of domain knowledge and also need lots of innovation and creative. If you work on some other competition like Kaggle or other competition before, it needs lots of, it's creative, like so-called is a magic feature. So basically that feature is like going to generate from other features based on your training data. Then like you have this kind of magic feature, like then you feed into your model. Basically the model itself is like something you give weights to each of the feature. It's combined with different features, then you get the result, right? So basically the feature part is like lots of people like tend to spend many time inside to do the feature constructions, to look into the data pipeline and to look into the data distributions and to say, okay, how I combine different features can have this kind of magic features. So this is like basically the pattern of how they solve the traditional machine learning problem. Then we jump into the deep learning. So if we look into the process right here, so for the deep learning process, it's going to skip this kind of step. Even sometimes you still need it, but most of the time is that you can skip most of part of the feature construction process. So the idea is that you hope the deep learning model going to learn this kind of feature construction or feature representations from your input directly. So here, like, that's why like sometimes like the people talk about deep learning, like say, okay, it's a black box or stuff like that, because basically you don't build a feature and then you let the model is like do it yourself. So but it's also a good part about that is it saves time, right? So you don't need to spend much more time like as a feature construction part. In fact, like in the following slides, like we were going to, for each task, we are going to both introduce the traditional machine learning method and also deep learning method. so you can tell the difference. The first task I'm going to introduce today is called NER, name entity recognitions. So the definition of the NER is it's an information extraction technique which identify or classify name entities in a text. So here is like a text, and you don't need to look into that details like, but the task is like, as mentioned, is to recognize the key information from that, such as a date, right? And also companies here like Google, IBM, Microsoft, you need to know is the organizations. So before we jump into the problem definition, the first one like we need to learn something is called label system. So there is various ways of the label, but one of the most common used label system is called IOB or BIO label system. So basically, IBO is stand of begin, inside, or outside. So basically, when you label something like that, the settings here, right? So what you did is that you have this kind of class labels here. Whether it's a person or like O stand for outside, it means it's not inside of your label. You don't care. It's like it's not belong to a certain specific label you define, and also you have an organization here, right? So, but why we need the B and I here, right? Begin and inside. The reason is that sometimes you have two of the entities inside of your settings. Here is an example: Michael Jordan and LeBron James are two of the greatest players in NBA history, right? For NBA, like it's okay, you just need one label to finish it. But because Michael Jordan and LeBron James, like it's two person, right? So basically, you want to label it separately. That's why you need this kind of begin and also inside label system to help you to recognize it's two person rather than just one person. And then like jumping into the question, it sounds like it's a pretty straightforward task, right? So we just build a dictionary. We put Michael Jordan in the dictionary, LeBron James in the dictionary is like indicate, okay, it's a person. And we build another dictionary is for organizations. We look into all the companies in the world, and we build, okay, this is organizations. It's in fact like people like tend to use that method at the beginning of the NLP stages, but then like it cannot solve some of the NER limitations. It's have limitations, and sometimes they cannot solve some problems. So here is one of examples. So the word, certain word is sometimes is can give different meanings or like belong to different types. So for examples here, like even for Shopee, it can be both organizations and locations, right? So the idea is that the first example given here, it's challenge and fun to work as a data science in Shopee, right? So here, like for high possibility, like people talk about Shopee, it stands for organization, right? But then like you have another example. There was a giant UFO landed as a rooftop of Shopee. So basically it's like, this one is for sure is a location rather than organizations. And so basically it's like same word, it's different types. So in order to you get the right label, you need to look into the content and also get the understanding about the sentence itself, right? That's why like make it hard. And the second one, like it's hard to find the boundary of the entities. So here is one of the example. Shopee is located near Singapore Kent Ridge Station, right? So basically, Kent Ridge Station is one of MRT stations, but it's also possibility you can begin your location as a Singapore, right? Singapore Kent Ridge Station. It also makes sense. So it's sometimes the boundaries can be so ambiguous, and also it's like people, even like for people, human beings like cannot define a hard boundary of that part. So that part is like makes the NER test also very hard. And also another one is how to know the class of unknown entities. It's out of word, right? So you never see this kind of word beforehand, and how you know like what's the meaning of that, right? So basically it's not inside your dictionary, but we still want to predict whether it's like belong to organization or all the stuffs. So basically, there is various ways to solve the problem. But beforehand, we jump into, okay, as mentioned, is like the NER is one of the classification problem. So basically, you have this kind of classification problem is that you have the features, which is actual x1 and x2, and most of the time you have more dimensions, right? X3, X4, X5, it's like lots of dimensions. Then based on all the features, right, the input, so-called input, you want to predict the labels, whether it's belong to a certain class, right? So basically the idea of the NER task is like quite straightforward. So you have the input, which is represented by either words, right? Or either embeddings, or whatever two vector we just introduced before, right? So that one is your input. So your output is going to be the labels, whether it's like beginning of a person or inside person, or like it's outside words, right? Something like that. For traditional machine learning method, it's like it's use something is called either it's like method called softmax or logistic regression to do the classification task. So basically, you have this kind of weights or the parameters here, which is have a two dimension. It's not two dimensions. To have a one dimension is going to be the number of the class. Another dimension is going to be the dimension of your input features. So imagine like the word true vector, you have the dimension of the is 64. Then like the d small d here is to be 64. Then for the class here is that you have let's say 5 types of class. Then the C here is going to be 5, right? So the idea is that similar like the one we introduced before, right? So you want to have this kind of probability given a words. Then you have this weight matrix here. You want given x, certain x is a word. You want the label is as close as to the real label labeled by the human beings, right? So the idea is like you use something like gradient design to update the weight slowly, and then you want to maximize the probability of the correct class, right? So basically, you don't want the things you predict is different from the real label. So here is going to be the first model going to introduce. It's called conditional random fields. So basically, conditional random fields is something like it's based on this kind of probability graph. So the idea is that I'm not going to jump into the mathematics part very detailedly, but it's just you guys can get a very basic understanding about this function here. It's called score functions. So F here like stand for features, right? So basically the feature is like going to depends on some of the input parameters. One is the input, one is the settings you have. So let's say like the examples we're going to give is like here, I don't have an example. It's like show the example give here, like work as a DS is a challenge in Shopee, right? So basically that is your settings. Then you have a I here, which is stand for the location of the word in the settings. And you also have a LI here, which stand for the label of this word in these specific positions. And also you have I minus one is the label of the previous words. So basically, you want to build this kind of feature feature functions based on your input sentence. So in fact, like lots of time, like when we build the conditional random fields, is how you define lots of features. So the idea of features like you can define something like this word, whether this word is uppercase or lowercase, or this words whether it's start with S or add of I. So it's something like you define inside of this kind of feature functions. And then the lambda here is going to represent how important the feature is going to be. So such as whether this word is a specific word is whether it's going to be important, right? So if it's like, so imagine like the feature function is something like true or false. If it's meets the feature function, let's say like, okay, this word is start as an add of I, it truly meet the feature function here, then it's like basically it's going to be 1. Then you have a lambda here is going to be, if that is true, how many weights you are going to give to it. So basically you want the score as high as possible, right? So basically you have the all the settings here. Then you do a combination of the labels. So here is a probability, right? So basically you have the settings, you have the label system. So let's say like we can do like, we can define like Shopee as an organization or locations. So for the organization label, you have one of the probability, right? So based on the score here, right? But also is like another potential is like Shopee can also be a location. So here is like you also have the score here, like if Shopee is a location. Then you sum all of the possibility here. Then you use the score of the certain label to divide by this one. So the idea is that you want the label as close as to your the true label by adjusting the lambda here, the feature importance here. So let's look into one of the case. So in fact, like for conditional random fields, there is two important features. One is like it's called transition features. So basically, it's something depends on your previous labels, right? So here, like how you read this one is like if last word is the previous word is beginning of organizations, so it's have a high possibility. Here is the lambda value I introduced before, right? It's how important it. So it's a how possibility or like how high possibility is going to be this word is inside of the organizations. So all these kind of examples, in fact, it's a real result from pre-training in a Spanish NER text. So you can see like basically the I organization. So it's inside of our organizations. It's tend to follow the beginning of the organizations, which is pretty makes sense, right? So most of the time you have the beginning of the certain label, then you further follow inside of labels, and also inside the label, next word can also be an inside of label because the organizations, sometimes you have such as some of the organizations, they have a long name, right? So you have several names. So basically this kind of relationship is called transition features. Another is called state features. So for the state features is something I mentioned it, like it's predefined by the either the developer itself, right? So basically, you use your pre-knowledge, you use your domain knowledge to define some of the features. So here is one of the examples, right? So whether the word lower is something like I don't know how to spell that, but like in fact this word is something that have meaning. It's represent some of broadcasting company in Spain. So basically, so if the word lower is this kind of word, is the model is tend to think, okay, it's a beginning of organizations. And also you have something like this, right? So it's like whether previous word, so it's a -1 is like whether previous word lower is I. If the previous word lower is I, it's have a high possibility it's going to be inside of all organizations. And also you have some features like this one is that whether it's this word is beginning of sentence. If it's beginning of sentence, it's a high possibility is going to be outside words, because the idea is like we dealing here, like most of the time dealing with organizations or locations, right? So basically people generally like put like organization as the beginning of their sentence, right? And also you have this kind of things is whether like the -2 from the ending of the two word is like to the end of the word is -e. So basically it's you can build lots of features based on your understanding of the language, also your pre-knowledge. So that is like something like similar to the task I mentioned here, right? For traditional machine learning or statistical model, you spend lots of time as a feature construction part. You use your innovation and you creative to create this kind of features, and then you put into the model, and you think, okay, it's hopefully it can generate is a good result. So that's the way like the CLF work, right? So the good part about this kind of traditional conditional random fields is like it's the result is always follow a certain pattern. As mentioned, it's inside of the organization. So most of the time, if you have the beginning of organization, after that, it's most of the time it's inside organizations. You seldom have something like start with a beginning of location, then it's like followed by inside of organizations. You seldom have this. Almost you don't have this kind of situations. But it's also have lots of limitations. Firstly, like it's need pre-knowledge to build the features, right? So basically you need to have domain knowledge. You need to understand the language and also need to understand the task in order to build a reasonable features. And also another thing is the sequence relationship are limited to a certain length, right? So the examples we gave is like basically it's only looking to the label of the previous words. But if you want to get some information from because when we talk about sentence, right? So basically the sentence, like the last word, it still have some information, like it's decided by your first word, right? So basically for this kind of conditional random fields, it cannot pass this kind of long sequence information when you go into your last word of the, let's say like the Shopee we want to predict, right? Another one is that feature space can be giant. So basically, every time you create a new feature, it's going to expand in lots of spaces, like such as you define the -1 word as one of your feature. So then you're going to have 24 more features. In fact, like you -1 word, whether it's like, in fact, it's not 24. Like if you define, let's say like the last character, whether it's like small case or uppercase, then like it's going to have 2 more features when like it's uppercase or like lowercase and something like that. So basically the space is going to expand dramatically when you have lots of features. And then we jump into our topic about neural network, right? So we mentioned, okay, use a traditional machine learning language, machine learning method, we have this kind of limitations. Then like whether we use deep learning model can truly like to solve the problem. So before we jump into the deep learning neurals, the first thing is like here like is a human neural. So how is like human neural work? Like you have this kind of neural here. So you have this kind of dendrites, right? So basically it's something like receive the information, such as I click my hand, then like I feel it's something like I tip my hand, then like it's something like the signal is like coming to the dendrite part. Then the dendrite part is going to go through the whole neural cells, the axon and also Schwanz, I'm not sure it's like million shells. Then you go to the next neurons, right? So you pass the information, the signal, electricity signal from this neuron until like pass one by one and until it's like going to your brain. And your brain know, okay, something is attached, or like when you look into something, you see, okay, here is a cup, or here is a laptop, or something like that. So like basically the deep learning neural like use something like similar, right? So the input is going to be the features. You have the X, Y, Z as your input. So the idea is that you have this kind of weight here. So W is represent like how much information you want to pass into next neurons, right? So basically you have this kind of gate here. So when I click here, right? So basically the weights W here is going to decide, okay, I'm going to put more weights at the X input and less weight at Y and Z. Then you do a sum here. Then you do some, it's so-called it's nonlinear activation function. Then you get the output. So the function, mathematical representation for the neural, in fact, is quite straightforward. So here the functions right here, right? So it's something like the linear regression, right? So basically, you have the W here, represents the weights you have is a W012 right here. And then you have your input is X, Y, Z. Then you weight is going to decide how much information you're going to give into next value H, right, hidden layer. So the B here is like it's it's a bias. It's basically it's always open. This information always going to give into the next layer, right? So and also you have a f here. Is like you can think is like why I need f here. The reason is that it's trying to increase the model complexity. It's because if your function here is like just a linear function, it's wx plus b. Imagine like you have this kind of deep learning. It's like the deep learning neural network is like one layer, right? So this kind of thing is like something here. Then you have this kind of a deep learning neural network, but even no matter how many times you sum this kind of basic function wtx plus b, it's always linear function, right? It's every time it's always is a wtx. It's like if you sum it 2 times, so it's 2 times of wtx, right? You don't have this kind of non-linear power to deal with some of the nonlinear situations, right? So basically the f here is called nonlinear activation functions, which is trying to give this kind of nonlinear power to your neurons, right? So some of the common use the activation functions, one is called sigmoid. So the sigmoid function, basically you can imagine like it's basically your input is from minus infinity and infinity. Then it's going to flat it into something between 0 and 1. So this one is called sigmoid functions. And also you can see it's a nonlinear functions, right? So another thing is called tangent edge. So it's something similar as a sigmoid, right? So basically looking to here is like, it's just expand that one to the -1 and 1. So basically for sigmoid, you are between 0 and 1, but for tangent edge, you just expand that one to the -1 and 1. In fact, it's you can do some transformations to transfer sigmoid into tangent edge. And then the last one is called ReLU, rectified linear unit. So basically the rectified linear unit is quite straightforward. It's 2 lines. So if it's smaller than 0, you just give a 0. If they're bigger than 0, you just give a x based on your input. In fact, this kind of rectified linear unit ReLU is very good result when you train a deep learning neural network. It's like use that one as activation functions. Right now, except for these 3, it also have other activation functions, but most of the time, like people talk about, it's like just mainly use ReLU or sigmoid for most of the time. And then like how you train a neural network, in fact, it's quite straightforward. And here is like one of the examples, one of the visualizations from TensorFlow. So basically here is your network, right? So you have your input x2x, right? x1 and x2. Then you have your 2 layers, 2 hidden layers. So basically something like that, right? So you have a hidden layer 1, then you just stack another layer, right? You have 2 layers. So the idea is that, okay, you pass the information to the first layers, then your first layer, you have 4 neurons. For each neuron is like something like that, right? So something like this one. So, and then you pass that one into the next layer, then you have the output, right? So here, like we can see, like it's a classification problem. Each of the color of the points represent one of the it's like certain class it belong to. So basically the idea is that is you want to train the function or the like neurons, the weights inside of the neurons, which is the W and B here. You want the functions to recognize some boundaries to split the 2 class, right? So basically you just it's use something is a gradient. So as mentioned, we use gradient design, but for deep neural network is use something like called back propagation to update the weights inside. So today I'm not going to introduce the back propagations. If you interest, you can just search back propagations. Then like a bunch of the tutorial you can find online. Then like after that, like you update all the weights inside, you can have this kind of clear boundary here, right? The white boundary here to split the 2 class. So outside is a class of the orange, and inside of the class of the blue. So here you can see like the power of the neural network, right? So here is the boundary is nonlinear. You cannot split that one by a straightforward line, right? By using this kind of very straightforward or like something naive like linear regression functions, you can achieve this kind of nonlinear boundary here by doing some trainings. And then like how we use this kind of neural network for our test, right? So basically, first one, like whether like we can use that one for the NER task we mentioned, the name entity recognitions. In fact, it can. So basically, at least all the information you may find useful here, right? So we already talk about the neurons and how we represent the neurons, and also the gradient design, how you update the weights or the parameters inside of your neural network. So the idea is that you have this kind of settings here as your input. Working in Shopee is happy, right? So basically, you want to do some classifications to see whether a certain word is belong to a certain class, right? So the idea, the first step is always, as mentioned, is always you transfer the word into a vector representations. So here is one of the examples, right? So you have working Shopee is happy, right? So the first step is that you do a word embedding. You transfer the word into vectors as your input. So you have this kind of X window, right? So the reason it's called window is because it's that you have a certain window, you just move step by step, right? So here like you have one of the vector. Here I use 2 dot to represent one of the. You have the vector represent for the work. You also have the vector represent for the in, and also Shopee is happy, right? So basically, you feed this kind of features, right? The embeddings, the vectors into next layer, right? So you have this kind of the neural functions here, right? Similar as this one here. You combine, so each line like you have, imagine you have a small weights here, right? So basically you control the weight, weight is going to control how many information you get from each of this kind of values. So you have one of the hidden layer. Then like you can stack one more layer, which is like similar like the last layer, right? So basically you get the information here. Then the last one like is use something similar as the one we introduced before, use the softmax functions, right? So basically you have a vector here, right? You imagine like it's a vector of values, right? So basically you want to know like to do a regular normalizations is like to see like what is the possibility is like going to give to a certain class, right? So basically you do this kind of softmax here. You calculate, okay, the total, like, let's say like it's 50, then like the value you have of the beginning of the organization is 40, then you have the 80% is going to be organizations, right? So basically it's you have this kind of word vector represent first, then you feed into the neurons, and then you have this kind of softmax and the last layer to do the classification task for you. So here's like one of the examples to show like you can use a neural network to solve some of our common use, common faced NER task. And also, so the next task I'm going to introduce is called language modeling. So language modeling is like also one of the common tasks that people facing. It's basically it's predict what word come next, right? So basically you have some of the word beforehand. ALP is fun to, then you fill into the rest of the information, whether it's fun to learn or it's fun to work or fun to study, right? But for sure you don't want to put a fun to exam here, right? So basically it's like how you, based on the previous words, you want to have the next words, right? So the mathematical representation of the problem is that you have this kind of previous word from 1 to t, right? So you have the word, first word is 1 and then until t. You want to predict what is the probability distribution of the next word with t minus 1, right? So basically you have the NLP is found and you want to predict whether the next word or what is going to be the next word. So the first model is going to introduce is called n-gram language model. So the idea is like of n-gram is something like it's chunk of n-consecutive words, right? So basically here like an example, if we want to deal with NLP is found to question mark, right? So basically for the unigram is like just one word, right? It's NLP or is or found or two. But when I like talk about diagrams, it's like going to be the two words together or two tokens together. It's like ALP is or is found or found two. You can also have the foregram, which is ALP is found, right? So the assumption of the n-gram language models that is that it's the word you're going to predict is only depends on the preceding n-1 words for the n-grams, right? So basically, let's say like you want to do a found to predict, right? So if you want to use a 3 gram and 3 gram, so it's going to only based on the previous two words you have. So here is the mathematic representation of the problem. So you want to do the probability distribution, right? Calculate the probability distribution given the previous t words. Then you want to have the predict the possibility of the the t plus 1 word, right, as a next position. So the idea is that it's you can say it's like subtract the rest of the information because it's a assumption is that it only depends on the previous n-1 words, right? So the idea is that it's also an unsupervised learning. So the idea is that you jump into all the settings, all the word you have, right? You basically you also such as you use Wikipedia or you use lots of text or like articles. You calculate how many like certain combination of n-gram happens, right? So you have this kind of conditional probability. So here is one of the examples, right? So it's maybe much more close, like clear if you look into the example. So ALP is found to what, right? So basically we want to use a 3 gram to do the language models. So basically you have a bunch of settings or articles. You look into it, you find out, okay, found true happen is like 1,000 times. Then the next task is that you look into the possibility is like how many times they happen for the trigram. So you look into that, you see, okay, found to learn is like happen about 500 times, and found to study is happen 300 times, and found to work is happen is like it's let's say like happen is like 200 times. Then you have this kind of probability distributions, right? You also look into other examples. The found to exam if it never happened, then the probability is going to be 0. So look into the data, right? You get this kind of probability distribution. So you can choose, okay, when we have this kind of found, NLP is found to, right? It's have a higher possibility is that the model is going to give the result it's going to learn, right? For NLP is found to learn compared to the NLP is found to exam. So here is a basic idea like how to you use n-gram language model to deal with this kind of language model modeling problem. So also like when like you calculate this kind of conditional probability, there is some tricks you may use when you calculate this kind of nominator, right? So it's have potential is never happened before, right? So basically it's going to have 0, but most time we trying to avoid 0. So we plus a small delta here to make it like it's not 0. So it's so-called smooth, right? So basically you give a very smaller delta here to avoid it, like the probability is 0. You still give some chance to it, to certain words, even if it's never happened before. And another one, like if your denominator is 0, right? So basically it's a mathematics, it's not going to pass it. So how you to deal with this kind of situation, right? So for this case, you look into all the texts, it never have something like happened before, like found true like never happened before. In fact, this kind of situation is happen when you have a very long grams, right? Imagine the longer your gram have, the higher possibility your denominator is going to be 0, right? So like in fact, it's seldom people say like NLP is found this sentence, right? And then on your denominator is going to be 0. So the idea is that use something that is called back off. So the idea is that if you deal with 4 grams, then you reduce that one into a 3 gram because you hope that it's a found true that it happened somewhere in your text. If it's like 3 grams still didn't happen before, you reduce that one to 2 gram, right? So for sure, like 2, like something you're going to have this kind of things inside. So this one is called back off. And then like, so here is like also like very traditional is like statistical modeling is to deal with the language model problem. Then like whether like we can use some deep learning model to solve the problem. In fact, the model is pretty similar as the NER task we had before, right? So beforehand is like you want to see do a classification problem, whether it's certain class, right? A certain tag. But right now, like you do something here, like to predict what is words is going to come next. So the test is pretty same. So here is like some improvements compared to n-gram. So first, you don't need to store all observed n-grams, but it still has some remaining limitations, such as you can see like why it's like called fixed window, right? Because like it's have certain windows to look into. And also when you expanding the windows, most time is like you tend to include more informations, but it also means the weight matrix you're going to have is going to be bigger, right? Another thing that is can't consider is order of the sequence, right? So basically, it doesn't matter is like the is before NLP or the before ACE because they don't have this kind of position information inside of this kind of neural network. And how we can solve this problem, in fact, is for sequence modeling is like most of the time we use something like this. It's called recursive neural network. So the idea is that you can have something, it's called hidden state to keep the sequence information. So basically, you can imagine it's a notebook, right? So the notebook is going to keep some of the information from the previous step, right? Let's say like you want to predict the last word, right, after 2, right? So the idea is that you have this kind of hidden state here, that it's passed step by step, step by. Then at the last stage, you also keep some information from the previous stage. So so the difference between the naive neural network here, right, is that it's for recursive neural network, it's going to have one more dimension, which is time here. So the ways you look into this gram, right? So for you have the input here is the NLP is found, right? So the first step is always same. You transfer that to a vector, which is the embeddings, right? So basically you use a vector to represent the words. Then you have something similar as the previous slides. You have this kind of weights, which is a transfer into another dimension of the information, right? The hidden state. But the idea of the recursive neural network is that you always keep this kind of information. It's like for next word, right, is here. It still have some of the information from the previous step, which is from the NLP here, right? So you pass the hidden state and you multiple with some weights, right, for the hidden states. Then you do a sum, right? So for this stage, you not only have the information from the A's here, you're also going to have the information from previous stage. So that is how the recursive neural network to keep the sequence information step by step, right? So when you come into the last word to here, you still have some information from the first step, right? So your first step, you pass here, you pass here, right? So every step you put some extra information inside. And so when you get the last stage, you also have the information. So basically the advantage of the recursive neural network is like it can deal with any length, right? So basically, imagine like you just reuse this kind of slot, right? One time by one time, right? And also, if you look into the sign here, WH and the WE, it don't have the time symbol here. It means all step is reuse the weights. It's didn't like, it's not like you have a 100, one sentence have 100 word, you're going to have 100 WE. It's not like that. It's just reuse of the weight parameters again and again. So it like save your saving space, right? So basically you just have a one-way matrix. And also but it's also have a disadvantage. So one of the problem is that because it's a sequence modeling. When you deal with sequence modeling, you always need to wait for the previous information, right? So it tend to make the whole process is slow. And also another thing is called vanishing gradient problem. So the vanishing gradient problem is that something like when you come to the last step, right? So every time you multiple with this kind of small WH here. So imagine like WH is like something like smaller is very small value. Then the idea is like step by step. And when you come to here, it's like you already lost all the information passed from the ALP. So basically, when you talk about two and you want to do the prediction regarding to what is next word, it's like the ALP impact to the result is already very small. That's one of the problem is facing by RNN. So before we jump into the next topic, next models. So here is like some examples generated by RNN regarding to the language modeling. So basically, like you just feed the text into the RNN model and do the training to get the WH, right? Then you can ask the model to generate some sentence for you. So like this one, like it's a RN Harry Potter. So basically, you train the RN on Harry Potter. Then like you have something like that. Voldemort smelled his throat loudly. What did it work? In fact, like, if you look into the sentence, like basically it's grammarly, like it looks good, right? Even though like some of the sentences like don't have meaning, or we cannot understand the meaning of that, but at least the grammarly like it looks pretty good. And then like the way like we solve the problem of the recursive neural network is they develop something like called LSTM, long short-term memory. So some key takeaway here like it's remember like last time the limitation of the RN is like the information tend to fade, right? When when you go to the end of the sentence, right? So whether we can have something like to keep the information. So the idea is that instead of you having hidden state, you also have something is called cell state. So the cell state is used to store the long-term information. Imagine the cell state is something like the notebook you have, right? So basically every day you look into the notebook, you tend to erase some information from your previous state, right? Because you're not going to use it. And you write down some new informations. And also if you want to do some task, you read into the information from your notebook, you try to generate the result. So basically that is the idea of the LSTM. So here is one of the graph I get from the Stanford MP class. It's quite straightforward. It's quite clear. So let's briefly introduce how it works. So basically, as a time t, you have this kind of input, right? It's basically you have the word vector here as your input. The things you want to have is like you have 3 gate here. It's called, so the main part is that you have 3 gate here is going to decide. One is like forget gate is going to decide what are you going to remove from your notebook, right? Going to remove from your cell content. And also you have this kind of input gate here is that what is the new information you are going to write into your notebook. And also you have this kind of output gate here is like what information on your notebook you want to use that one to do some task, right? So basically you have this kind of 3 gate here. So looking into the first gate here is forget gate, right? So basically you have the input hidden state from the previous step, right? And also you have the input from your current task, right? So basically you have this kind of forget gate is decide, okay, how much information we want to remove from the cell state, remove from your clean from your notebook, right? So basically this is the target of the forget gate. Then you have the second part is the input gate. So the input gate is input gate plus also the new cell content. So it's like it's based on your input and also the hidden state. So you have something you want to write into the book, you write into the notebook, right? Write into your cell state. And also you have this kind of input gate to control, okay, how much information I'm going to write into the cell state. So basically here is the information you are going to add into the cell state. Is the new information you add into your notebook. Then you also have this kind of output gate. It's like based on your cell state. So if you look into the output gate, it's like going to based on your cell state and also based on all the information, new information you have, you're going to get the output. So basically, it's based on the historical notebook and also all the information you on the notebook, right? So the one the historical one you have and also the new information you have, you give some output. So that's the idea of the LSTM. So in fact, the forget gate is like, if you imagine like if we close down the forget gate, it's like every time it's like I never remove something from my notebook, then like it's going to keep all the information, right? Historical information inside. So that's the idea, is like how you use this kind of LSTM to solve the vanishing gradient problem. So here is like one of the examples. Basically, you have this kind of sequence, and then you get as a result, right? So the advantage of the LSTM is like it's makes it easier for RNN to preserve information over many times, and also so basically it's one of the standard method is using for most of NLP tasks. And if you deal with this kind of secret modeling, is that most of the time LSTM is first one if you have enough training data, and most of the time it's going to tend to generate pretty good result. But also it have limitations, doesn't guarantee there's no vanishing gradient problem. So here is one of structures how you use LSTM to deal with NER text, because we don't have enough time, so I'm not going to jump into this one detailedly. But then like we jump into something is called transfer learning, right? So all the LSTM or RNN we mentioned is like you need to have lots of pre-trained data, and then you need lots of training data to do the task, right? So the idea of the transfer learning is that whether we can learn from other data source and reuse some of the weights. In fact, transfer learning is very famous idea for the computer vision. So in fact, like lots of model in computer vision, they use transfer learning ideas. Example is that you have lots of image already pre-labeled as whether it's cat or dog, right? So it's for generate task, right? So you have this kind of convolution layer here to do the task. So whether like when we jump into a new task, such as you have the X-ray image, right? You want to see whether it's like the bone is fractural, like it's malignant, whether it's like the bone is okay. So, but you don't have enough image to train a very deep neural network, right? So whether we can directly use weights from this kind of pre-trained model, right? So then like we just do some, it's like called tuning some of the weights, or like add into some new layer to finish our task. So in fact, for NLP, like whether like we can use the similar idea, right, in NLP to do the task. Basically, you have the Wikipedia, right? So and also you have lots of fictions and lots of writing text in your high school books, right? So it's all data set. Whether we have some model is like pre-trained on this kind of text, then like when you have this kind of specific task, you just directly jump into and you reuse some of the weights is pre-trained. In fact, it's like half. in fact, also it's like a big family. It's if you look into it, like it's something called Elmo, and also have something like the GPT we mentioned before. But one of the main is like the most common use, or the most famous one is like called BERT, right? You can see all the subtask is from BERT here. So the BERT is like it's a transfer learning task. So it's stand for bidirectional encoder representation from transformers. So it's very confused, right? Word like basically you have the encoder here, and also you have a transformer here. So right now, like you can just imagine like transformer like it's a function box you can use, right? So basically the BERT use this kind of encoder function instead of the function box to pre-train in lots of tasks, lots of texts and articles as I mentioned, Wikipedia and Google News, right? So basically, this kind of giant model, right? It's use some use some data is like to do some pre-trained tasks. Two of the tasks is one is called mask language modeling. So it's basically you random mask some of words is such as it's something similar as a middle school task, right? So you have a one sentence, you just randomly your teacher randomly take out some of the words, then you to fill it into the word. So basically, it's a mask language modeling task for the BERT. Another one is next sentence predictions. So basically, you have two sentences. You predict whether it's like next the sentence is like belong to is should next to this first sentence, right? So basically, this kind of BERT is pre-trained on these two tests in lots of data you have. In fact, it's they like for BERT is I have two base model. One is like called BERT base, so it have 1100 million parameters. It's law. It's a giant model, and also another one is BERT large. It's 340 million parameters. But in fact, for this kind of model, like how fast is it going to, how long time is it going to take to train? It's like if you search online, here is the result it gave you 53 minutes. Then you say, okay, it's not too bad, right? It's 53 minutes. I drink coffee and then I finish. But then you look into that, it's like NVIDIA uses 1,472 NVIDIA 100 GPUs to train that. So if you're not familiar with the GPU stuff, right? So for V100, it's called $8,000 right now on for a single V100. So basically, like most of the time, like if you have one like such GPU as a V100, it's already very happy, right? But NVIDIA they use this so many GPUs to pre-train the model, to train the model in order to have a decent weights. So it's similar as the computer vision task, right? So it's seldom people is like train the model from start. It's just they just use it for specific tasks. They use that one for tuning. So here is the example, right? So basically, you reuse all the weights inside. Then you for specific task, you choose a certain elements from the model, and you do a fine tune of that. So basically, here is like for sentence pair classification. It's like it's a classification problem. You to say whether it's a true or false, right? You take the say signal here to do the classification task, and also for the NER task we mentioned, right? So basically, it's something like that. You just have the final layers is going to be your softmax layer to do the classification problem. Then you can reuse all the weights the NVIDIA or Google already pre-trained for you. So you save a bunch of time. Then like we have a small time to introduce popular NLP engineering frameworks. So one is the NLTK, which is you can do is use that one for tokenizations and lamentations and lots of tasks, and also Spacey, which is also a general NLP tools. You can use that, and also GenSum. GenSum is it's have a pre-trained vectors inside, so you can reuse it. Another one is Hugging Face. Hugging Face is basically they have lots of pre-trained models such as BERT, right? So for different language, so you can directly use the models rather than train from start. So all this 4 is like for Python. For Java 1 is like called Stanford Core NLP. So it's also have it's very powerful and can do tokenizations and most of the tasks we mentioned in previous slides. And also some useful learning materials. If you're interested about NLP, Stanford CS 224, and is like for sure you need to take it. Very good class. And also for deep learning AI from Coursera, they also have this kind of specializations for natural language processing. And some of the books you may find like useful is like natural language processing with PyTorch, lots of examples inside, and also other 2 books. And all the reference mentioned today in case you need. So I think let's see, like I don't think we have a very good time, long time to answer all the questions. Let me select several ones for the several questions. So one of the questions like interesting is like, can word embedding be different in language? For sure, it's like going to be different for different language, right? So because the language is the word embedding for Chinese English, for sure you cannot use for Chinese, right? Because you don't have the mapping information. So it's basically it's just the word embedding. You can imagine it's the dictionary. You have the tokens, then you have the vectors, right? So basically, you need to have this kind of mapping information inside to do the word embeddings. And also, let me see. To train a word embedding model, how much data we need to put into the model? It's in fact it's so the more data you have, it tend to give a better result, right? So for the one I mentioned is like for gloves and all the models they have, in fact they train lots of train on lots of materials. That's why it like we seldom to train the embedding ourselves. But if you have enough training data and enough text, you can train an embedding model yourself. Sometimes it's going to give a better result. But also, like if you want to reuse some of the models, right? So as a transfer model mentioned, the bird, you cannot, because the bird, remember is like for most of model, they have this kind of embedding layers as the first layer of the input, right? So if you use bird or you use other transfer model as Elmo, you cannot use your customized embeddings because the inside of the parameters as mentioned, right? All the weights is already pre-trained, right? Pre-trained is like all the weights they pre-trained is based on the vectors they have. So you need to use the vector, what vector they have, what embedding they have before. If you change that and you have the vectors, use the vectors you have, then like it's going to have something is like you're going to rule the model, right? So basically that one like you don't want to do that for the transfer learnings. Let's see. I think we run off the time. So I think that you guys like still have lots of questions, and happy like you guys gave so many questions, but sadly we don't have enough time to answer one by one. But for sure, like after this sharing session or this workshop, you can jump into the material I mentioned. Basically these materials, right? So or search online. But most of the time you can get a good answer regarding to most of the questions you have. Yeah, I think. Thank you guys for today's listening. Is like I know it's like 2 hours, like pretty long for most of your guys, and also just hope you learn something from this workshop, and hope all the best to the competitions, and good luck.